On October 18, 1919, Arthur Eddington proved Einstein's theory of general relativity with an experiment that anyone can do. Okay, maybe not anyone, but at least anyone with access to some sextants and some clouds. It was the first time we had proof that space was curved. But what does any of this have to do with red giants? Well, the answer is everything, because it turns out there's another way of telling whether space is curved or not. And that method relies on stars that are so big they make Betelgeuse look small. In case you weren't aware, our sun will one day die an excruciating death. It will run out of hydrogen fuel, puff up into a red giant, and gobble up nearby planets before being flung into outer space as a white dwarf. But that is nothing compared to the truly ginormous red giants that lurk in the farthest reaches of our galaxy. These behemoths are around 1 billion kilometers in diameter, which is over 1,000 times larger than the sun. In fact, if you replace the sun with a red giant, you could fit over 1 million of our suns inside one of those things. It's just insane. And these monsters are so bright that even from Earth, we can see them with the naked eye. Take Arcturus, for example. This red giant is located 37 light-years away and has a magnitude of -0.04. To put that into perspective, you need a magnitude of about 6 to be visible to the unaided eye. And many red giants like Arcturus have magnitudes far brighter than that. But how exactly do we figure out the size of a star? If you were back in school when I was teaching, you may remember something called similar triangles. Similar triangles are two triangles that have the same shape but different sizes. The corresponding sides of the triangles are proportional to each other. Like if you have two similar triangles, a small triangle and a big triangle. The ratio between the base and the height of the small triangle equals the ratio between the base and the height of the big triangle. And we use this idea to figure out the size of stars by comparing their apparent brightness with their absolute brightness. Apparent brightness is how bright a star appears to us here on Earth, while absolute brightness is how bright it would appear if it were located a standard distance away, like 10 parsecs, which is just a fancy way of saying 32.6 light-years. Once we know a star's apparent brightness, we can use similar triangles to compare that with its absolute brightness and calculate how far away it is. For instance, let's say we have a candle flame. On its own, the flame isn't very bright, but if you take a magnifying glass and focus the light onto a wall, it looks brighter. And the brighter you make the flame appear, the farther away the actual candle must be. The trick is that we already know how bright the candle is on its own, which is its absolute brightness. We can also measure how bright it appears, which is its apparent brightness. So if we divide the apparent brightness by the absolute brightness, we get the square of the distance to the star. We can measure a star's apparent brightness pretty easily by determining how bright it looks next to a star whose absolute brightness we already know. Stars whose absolute brightness we know are called standard candles. One common type of standard candle is a Cepheid variable. These stars pulsate and change in brightness, but they do so predictably. As the star expands, it gets brighter until the surface of the star reaches 10,000 degrees Celsius. At that point, the star is emitting light at maximum efficiency, and so it can only get dimmer as it contracts again. And because they're so predictable, astronomers can match a Cepheid variable, its period of pulsation, to its luminosity class, and use that to determine its absolute brightness. Astronomers can then observe a distant galaxy containing a bunch of Cepheid variables and use similar triangles to work out how far away it is. This is called the main sequence method. You identify a star with a known absolute brightness, compare its apparent brightness with that of other stars, then work out how far away the others are. But there's another way to measure the brightness of stars that doesn't rely on knowing their distances, and that's through something called stellar parallax. Stellar parallax is the apparent shift in position of an object when viewed from two different locations. Let's say you're standing still, and a car is driving past you. The car appears to move faster the closer it is to you. Now imagine you're standing on a merry-go-round instead. Even though you're moving, the car seems to move more slowly as it passes. That's because your frame of reference changed. Parallax works the same way. When you stand in one place, it seems like the stars close to the sun are moving around it in circles. But once you leave that spot, like by traveling to a different planet, the stars seem to be moving around you in circles. It's all relative. In other words, astronomers can measure how much the positions of nearby stars change, when observed from two different points in Earth's orbit around the Sun. Because we know the size of Earth's orbit, we can use similar triangles to work out the distances to those stars. So stellar parallax is another way of measuring distance without using standard candles. And stellar parallax measurements have revealed that space is curved. Back in 1929, Edwin Hubble discovered that the farther away a galaxy is, the faster it is receding from us. It seemed as if the entire universe was expanding, which led to the Big Bang theory we accept today. But there was a problem with Hubble's discovery. He had no idea if space was flat, positively curved like a sphere, or negatively curved like a saddle. All he knew was that space was getting bigger. In 1938, Austrian astronomer Karl Schwarzschild found a solution to Einstein's equations of general relativity that described a black hole. He also came up with a way of determining whether space was flat, positively curved, or negatively curved. His solution predicted three possible scenarios based on the value of a constant called the cosmological constant, represented by the letter lambda. If lambda was equal to 0, space was flat. If lambda was greater than 0, space was positively curved, and if lambda was less than 0, space was negatively curved. So in order to find out the shape of space, we just needed to find lambda. We can do that with a little trigonometry. Imagine a beam of light traveling through space from A to B. According to Einstein's theory of special relativity, light always travels at the same speed, regardless of the observer's frame of reference. So it takes 10 seconds for light to travel from A to B, no matter where you're watching from. However, if we consider the same scenario in general relativity, the situation changes dramatically. Let us say that the beam of light travels from A to B in a universe that is positively curved like a sphere. Then the light beam doesn't travel in a straight line, but follows a longer path, so it takes more than 10 seconds for the light to travel from A to B. Conversely, if the universe is negatively curved like a saddle, the light beam travels from A to B in less than 10 seconds. All we need to do is measure the time it takes for light to travel from A to B, and we can work out whether space is flat, positively curved, or negatively curved. That's basically it. And as you might have guessed, this method relies on stars to measure the time it takes for light to travel from A to B. But there's a slight problem. The stars aren't actually in the same place every year. They orbit the galactic center, and that means that if we try to use a star that's far away as our reference, point the light may not travel from A to B in 10 seconds one year, but it will the next year. That's why astronomers use red giants as their reference points. Red giants are so massive that their orbits around the galaxy are nearly circular. That makes them ideal for measuring tiny changes in space over time. In 2003, astronomers used red giants to measure the time it took light to travel from A to B. And they found that space is flat to within 95% certainty. However, a few years later, measurements taken by the Wilkinson microwave anisotropy probe showed that the cosmos is only 0.14% away from being flat, meaning that the shape of space is either flat or positively curved. And that was another step forward in proving Einstein's theory of general relativity. There's been a lot of talk lately about how Einstein's theories have been proven wrong, but that isn't quite true. Einstein's theories have never been disproven. In fact, they've stood the test of time and continue to explain our observations of the universe to this day. Physicists simply found a way to describe gravity more accurately, but that doesn't mean Einstein was wrong. It's just science. You know, scientists learn new things all the time. It's part of the process. And if you want to be part of that process, you should check out Brilliant.org. Brilliant is an online learning platform with thousands of lessons in science, computer science, and math, and they've recently added a course on large language models. It covers how LLMs work, how they're trained, and what the current limitations are. You can learn all this by answering questions, running code snippets, and building your own LLM from scratch. Thanks for watching this video, and thanks to our sponsor for supporting it.